Good afternoon, everybody. Thank you for dragging yourselves away from that delicious lunch to come hear me talk about distributed consensus. My name is Heidi Howard. I'm a research fellow at the University of Cambridge. I'm based in the Systems Research Group in the Department of Computer Science, and I'm fascinated with the problem of distributed consensus. Distributed consensus is the problem of how to decide a value or a series of values in a distributed system. It does not assume that the participants in the system are reliable or that the system itself is synchronous. It's a little bit of a tricky problem to solve, but if we can solve it, we can do so much with it. We can build systems that provide the strongest consistency guarantees, like linearizability, without relying on the underlying participants to be available to us or to act synchronously. And this is why I love distributed consensus. I'm going to be talking about consensus today. It's a famously tricky topic. If you don't understand everything first time, do not worry, it is not your fault. Do approach me in person, contact me by email, contact me by Twitter. I'm very happy to talk to people about consensus and helping them to understand it. So we're here today, well, at least I'm here today. I hope you're all here today for the same reason, because we believe in the dream of what distributed systems can provide. We believe these systems can be scalable and low latency, adaptable and versatile. We also want them to tolerate faults and be dependable and very reliable. And we want them to be correct. We want them to behave as we as users would expect. And we want to be able to reason and understand what's going on with these systems, especially when they're misbehaving. But you can't have everything in life. You only have to look at the academic literature from before I was even born to know that we're not going to be able to achieve all of these things. So these are two brilliant papers. I love this paper here on the left. 100 impossibility proofs for distributed computing. That's it. It's just 100 things you can't do. That's what the paper is. And on the right, we've got this paper, The Impossibility of Distributed Consensus with One Faulty Process. This is known as the FLP result, and this is the paper that said that solving distributed consensus was impossible. This is the paper, from my perspective, that founded the field of distributed consensus. So if you want researchers to spend decades working on your problem, write a paper claiming it's impossible. And it's not just the academic literature that says that we're not going to be able to get all these things. We see this in practice too. So I absolutely love this figure. I use it to give my students nightmares. Don't worry if you can't read everything that's on it. That's not the point. This comes from a really brilliant survey paper, which is called Consistency in Non-Transactional Distributed Storage Systems. And it was published in the ACM Computing Surveys. And it gives an overview of the different consistency guarantees that are provided only in non-transactional distributed systems. There's a lot of them. This is confusing. This confuses me. There's over 60 different consistency models that are covered in this survey paper. At the very top, if you can't see it, is linearizability. So this is the guarantee that when we send a request into our system, it will appear as if it's been executed atomically between when we sent the request and when we got the response. This guarantee means we can reason about our distributed system as if it wasn't distributed at all. That's absolutely amazing, and that's a lot easier to understand than all of these other things. But all these other things exist because there's a performance penalty to guaranteeing linearizability in practice. What I'm going to be talking about today is distributed consensus. It's a simple problem, or seemingly simple problem, of how to decide a single value. In this talk, we're going to be talking about a system with two different components. Servers, these are the participants that store the value, and clients, these are the participants that are going to propose values. That's it. The servers in the system are the kind of passive participants, and the clients are the active participants that are going to do all of the work. If you're familiar with other consensus algorithms such as Paxos, the server in this case is analogous to the acceptors in Paxos, and the clients are analogous to the proposers and learners. I've been criticized for not making this clear enough in my talk, so I will make this overly clear. This is not a blockchain talk. There is a whole field of consensus known as Byzantine fault tolerance. It's a fascinating area, but this is not the topic of this talk. I'm going to make the huge simplifying assumption that the participants in this system are going to do as I tell them. They are going to follow the algorithm. They might be slow, they might stop, hopefully they'll recover in the future, maybe they won't, but they're not going to go rogue, they're not going to be malicious, and they're not going to be acting arbitrarily. Just wanted to make that clear. So the requirements of consensus are twofold. Firstly, we have the safety requirement. All clients must learn the same decided value. If we had a consensus algorithm that was basically just an echo server, whatever client proposes, you send back to that client the same value, that wouldn't solve consensus, it wouldn't be safe, it wouldn't be useful either. And we have the progress guarantee. This says that eventually, all clients must learn the decided value. What's really important here, and what makes this seemingly very simple problem not so simple, is that safety must hold regardless of unreliability and asynchrony in the system. So that means safety must hold regardless of how many of the participants fail, regardless of whether messages are lost, regardless of how long it takes for a message to get there. We can't assume that our clocks are even synchronized. Safety must hold whatever happens. When it comes to progress, however, we do assume that eventually, if everything comes up, messages are sending, the system is healthy and good, then consensus will terminate. But safety here is unconditional. And there's a very well-established solution to this, whose author is at this conference, and this is the part-time parliament algorithm. So this famous paper outlines a solution to distributed consensus that is widely used in practice today. The algorithm uses two phases, and each phase uses majority quorums. Whilst this algorithm is talked about a lot, in practice, its optimization of it, called multi-Paxos, is what is actually widely used and is very similar to algorithms that you might be familiar with, like Raft. In that algorithm, the first phase basically elects one of the participants as a leader, and then you can achieve consensus in just one round trip. So, what do people have to say about this algorithm that's changed how we construct distributed systems? Well, Lamport says that the Paxos algorithm is very simple. Brilliant. The Paxos algorithm is among the simplest and most obvious of algorithms. Great. This consensus algorithm follows almost unavoidably from the properties you want to satisfy. If you just sit and think hard enough about consensus, you will derive Paxos. It will be that obvious to you. Unfortunately, this view isn't shared by everybody. Consensus has had a resurgence in recent years due to the Raft paper. And this is what the Raft paper's authors have to say about Paxos. Paxos is extremely difficult to understand. Few people succeed in understanding it, and only with great effort. We found few people were comfortable with Paxos, even among seasoned researchers. We conclude that Paxos does not provide a good foundation for either building systems or for education. That's quite a damning indictment. So, when it comes to Paxos, I believe there's two key limitations. Firstly, Paxos is subtle. My evidence for that is the claims that we just saw on the previous slide. And secondly, Paxos is slow. Requiring the majority of people to agree to something before you do anything is slow. It's never going to perform that well. In fact, this common optimization of multi-Paxos, where one of the participants is the leader, is always going to be very limited in terms of performance because you've got one participant who has to do everything, who has to be the center of a system. These systems are the opposite to a scalable system. If you add more nodes to a consensus system, the performance gets worse. The best performing consensus system uses one node. Anything beyond that, things are going to get worse. And since the publication of Paxos, there has been, I'm doing a survey at the moment, 150 other consensus algorithms that have been proposed. And broadly, these algorithms are trying to solve one of these two problems. They're either the raft consensus algorithm, and they're trying to improve on the subtlety, or they're something like egalitarian Paxos, and they're trying to improve on performance. Today, however, I'm going to have a go at trying to deal with both of these, because dealing with only one of these isn't actually going to fundamentally solve the problem. We have all these high-performing consensus algorithms, but very few people understand them, and so they can't deploy them. And consensus algorithms aren't that understandable, so optimizing them is really difficult, because if you optimize them, how do you know whether you violated correctness or not? So in today's talk, we're going to go right down and back to basics. And we're going to differ from the usual explanations of consensus in two key ways. Firstly, immutability. When it comes to consensus, there's a lot of state to keep in your head. It's difficult to know what's going on, and I certainly do struggle with it. So I'm going to only use immutable state. I'm going to use a series of write-once registers. That makes it easier to reason about what's happening in the system, because if you read a register that's immutable and it's been written to, that read will never be stale, regardless of the asynchrony in the system. And secondly, it was a little bit hard to find a word for this, I'm going to be using generality. And by that I mean I'm going to be talking in high-level terms. Instead of narrowing straight down to a very specific algorithm to solve a very specific problem, I'm going to be looking at what are the rules that govern consensus algorithms. Instead of coming up with one algorithm, can we come up with a family of algorithms that could be specialized to different problems? As I said at the beginning, I come from a systems group, so when I presented this to them, they were like, what are you doing, crazy person? If you want to improve performance, you specialize. But what I'm aiming to do here is to generalize such that engineers have choices about the trade-offs they want to make in distributed systems. So an engineer can choose, this is the level of fault tolerance I want, versus this is the level of performance I want. These are the compromises I'm willing to make, and these are the ones I'm not. So the idea is to come up with a version of Paxos that's as flexible as possible. So today's talk is going to be proceed in three parts. So firstly, we're going to reframe the problem of distributed consensus using write-once registers. This is where we're going to see this immutability in practice. In the second part, I'm going to explain the kind of infamous Paxos algorithm. And I'm also going to generalize and weaken some of the requirements of this algorithm. And in the third part, I'm going to put this to practice. I'm going to propose a variant of Paxos that I think in some systems could be very useful. This is not to say that I have an alternative consensus algorithm that's going to be better than Paxos in every possible scenario, but instead to say that there are many different options out there, and that I want you guys as engineers to be informed about the different options that there are for your different systems. Right, so let's dive in. If we only had one server, achieving consensus would be straightforward. Here I've got a single server, S0, and it's got a register, this little white box. Client comes along, and it wants to propose a value. So it tells the server, I propose a value, and that value is A. The server writes the value into its register and responds to the client. I accepted your proposal. The value that's been decided is A. Client goes away happy, and another client comes along. This client says, I want to propose a value. This value is B. And the server says, sorry, value's already been decided. The value was A, because I accepted A already. Through this process, both clients learn that the decided value is A. This is a solution to consensus. It has those two properties we saw earlier. It's safe, as long as that register is in persistent storage, and it guarantees progress, as long as that server's up. But that progress is conditional on that one server being up. And we love distributed systems, so let's make this system distributed and have 3 servers instead. This is where things get a little bit trickier, but not too bad. let's propose an algorithm. Clients come and they're going to tell all the servers what their proposal is. These servers will accept the first proposal they see and respond to the client. And because we know a little bit about distributed systems, we're not going to require clients to hear from all the servers. Instead, we're going to only require them to hear from a majority of servers. So once a client gets that accepted message from 2 servers, then that's job done. And since majorities will intersect, then we're never going to end up deciding more than one value. So that was a lot to take in, so let's look at an example. Here we have client 0. They've got a value they want to propose, which is A, and so they're going to send this message, propose A, to all of the servers. Each of these servers writes the value A into that one and only register and responds to the client. Once the client has seen 2 responses, then it knows the value A has been decided. Another client comes along. This time they send the message propose B, and the servers look in their registers and say, sorry, you're out of luck. I already decided a value, and that value was A. This algorithm is a safe solution to consensus because you're only ever going to end up deciding one value. However, this algorithm doesn't satisfy the progress property because there's nothing that prevents us from ending up in a situation like this. In this case, each of 3 clients has spoken to a different server first. One server's voted for value A, another server's voted for value B, and another server's voted for value C. I said at the beginning that these registers were immutable, so there's nothing we can do. We failed to reach consensus, and that's the end of it. The obvious solution here would be to make these registers mutable. The problem is then it gets difficult to reason about what's going on in the system. So instead of going down that road, what I'm going to do is I'm going to introduce more registers. In fact, in theory, I'm going to say there's an infinite number of registers that there could exist. And what we're going to do is we're going to try to reach consensus using the first set of registers on each server. And if that doesn't work, we've got a second chance. We'll try it on the next set. If that doesn't work, we'll try again on the next set. And to save me from drawing out way too many diagrams, I'm going to introduce this idea of a state table. A state table just simply shows the registers that are in the system. So each column represents one of the servers. In this case, we have 3 servers. And each row represents one of the registers. The registers can be in one of 3 states. So either the registers can contain a value, like A, B, or C. The register could be unwritten, so nobody's written to it yet. Or the register can contain a special null value, which we'll talk about later, but is denoted using this hyphen. So we've got a system where clients can come along and they can write to these registers and servers, but what's actually happening? When do we reach consensus? When have we done enough work? When are there enough copies of a value for us to say, right, for a client, to say, right, we've done this, we've reached consensus, I have learned that this was the value. And this is the rule that we're going to apply. A value is decided when it has been written to the same register on a subset of servers, known as a quorum. Now, I'll flag here that when I say the word quorum here, I simply mean a non-empty subset of servers. If you're familiar with distributed systems, when you hear quorums, you'll think read-write quorums or intersecting quorums. Later, we'll assess the question of whether these quorums need to intersect or not. But for now, you can use any non-empty subset of servers that you want to use. And so a client comes along, they're writing into these registers however they feel like, and as soon as they learn that a quorum contains that value, of the same value, they learn that that value has been decided. And at the start, I said we're going to use immutability and we're going to use generality. So this is where the generality aspect comes in. We're going to express the quorums that a given system is using a quorum table. It's simply a table that maps registers to quorums. So in this case, register set 0 maps to 2 servers in a system of 4. Register set 1 maps to a different 2. That's fine, they don't have to intersect. And registers 2 onwards map to either of the 2 pairs. You can replace this with any subsets you want. That's where the kind of generality comes in. And later we'll look at which different quorums you might want to use and why. So we can combine the state table that we saw and the quorum table to look at a system and work out whether it's reached consensus. And we call this a decision table. There's a theme here, it's tables. So it maps registers to quorums, and then it says, what state is that quorum in? One state a quorum could be in is no decision. That means that 2 registers in that quorum contain different values, for example. Because these registers are immutable, whatever happens, you're never going to be able to reach a decision in that quorum. That quorum is stuck. That quorum was never going to reach consensus. On the other hand, we have a state which is yes. Yes, all the registers contain the same value, in this case A, and consensus has been reached. Another state is any decision. If you've not written to any registers, that quorum could do anything. Maybe it will reach a decision. Maybe it won't reach a decision. Anything can happen. The world is that quorum's oyster. And then there's maybe. This is kind of an in-between between any and yes and no. This means that at least one of the registers contains a value, and the other registers are unwritten. Should a client come along and write that value into the rest of the registers in that quorum, it would reach a decision. But it might never reach a decision. Perhaps a client would write a different value into one of those empty registers. So our goal in the system is to go from any, because all registers will start in any, because all quorums will start in any, because initially all registers are empty. And the idea is to get these quorums to the state of yes. So that was a lot to take in, so let's look at some examples. We've got our quorum table, and I'm going to fall back to using majority quorums regardless of the registers. And here's an example state table. We've got 3 servers in this system, and A has been written in 3 times. And we can look by combining these 2 things to say, have we reached consensus? And the answer here is yes, we have reached consensus. At register 0, we've reached consensus using the quorum S1 and S2. The remaining quorums will not be able to reach consensus, except for R1 quorum S1, S2, where if you look in the state, one of them contains A and the other has been unwritten. So it might decide A, or it won't make a decision. But there's no way that's going to decide China. So here's a different example for you. This time we're varying the quorums based on the register stats. So here we have a system of 4 servers, and register set R0 contains all 4 servers. Register set R1 onwards contain one of 2 pairs. And here's an example of what the state of a system might look like. Here, we've reached consensus. In fact, we've reached consensus twice, and that's perfectly okay. Multiple quorums are able to reach a decision as long as all those decisions are for the same value. So here we see that a decision has been reached in register set R1, and the same decision has been reached again in register set R2. At this point, we've not placed any restrictions on what clients can do. They can come and read and write whatever registers they want. This algorithm is in no way safe. So we can decide multiple values. So here's an example. We've got 2 different values that have been decided in the register set R1. The value C and the value A. So this algorithm is not solving consensus for us. In fact, we can also reach different decisions in different register sets as well. So here, value A is decided in register set R0, and then value B is decided in register set R1. So we haven't really achieved anything yet. We're going to have to place some restrictions on these clients before we let them write to ensure that all the decisions that are reached are for the same value. And this is the rule we're going to make clients follow. Before a client writes a value to register I, it must ensure that no other values could be decided in registers 0 to I. So none of the register sets before my own or in the same register set as me can decide a different value. If every client does this check before it writes, then inductively we know that all decisions will be for the same value. Now, it's one thing to state it, it's another thing to actually do this in practice. So in the second section of this talk, we're going to talk about how Paxos actually satisfies this rule. So we're going to split that safety criteria up into two parts. The first part is that before a client writes a value to a register I, it must ensure that no other values can be decided in the same register I. If that register set only has one quorum, then that's fine. We know that it's only going to reach one decision. But if it has multiple quorums, we're going to have to do a little bit of work to ensure that those quorums decide the same value. And secondly, we require clients to check previous register sets to ensure that no different values have been decided in those either. So we'll deal with the first one first. And this is how it's addressed by Paxos. We allocate registers to clients in a round-robin fashion, for example. And we say to clients, you can only write into the registers that you have been allocated. And when you write into a register, only write one value to that register. This means that any given register set is only going to have one value written into it. And if only one value can be present in a register set, only one value can be decided by the quorums in that register set. So that's the first of these two safety criteria dealt with. Let's take a look at the second. For this, we use a rule known as the value selection rule. This says that a client must read one register from each of the quorums for register sets 0 to I-1. And when they do that read, they need to check two things. Firstly, they need to check that all those registers have been written. If you find one of these unwritten registers, then that quorum may be stuck in any state where it could decide anything. You need to basically lock down that quorum, you need to freeze it, and say, you will not reach a decision, I'm going to write something there. And since we have all these rules about writing things, what do we write there? How do we freeze a quorum? How do we stop it from reaching a decision? This is where that null value that we saw earlier comes in. If you want to just fill a register quickly and easily, you can just write null to it. There's no rules about writing null. Secondly, we're going to read what's in these registers. And the client must write the value from the greatest register it has seen. So that deals with the second of these two criteria. Now we're going to delve a little deeper and look at the actual details of how Paxos implements these two rules. The main thing I want you to take away is that Paxos is a two-phase algorithm. The role of the first phase is to basically ensure the safety of the second phase. In the first phase, we implement these two rules. We implement the register allocation rule and the value selection rule. And the output of the first phase is here is a value, and here is a register set you can write it to, and that those will be safe. In the second phase, the client actually does the work of achieving consensus. The client writes a value. And in the examples on these slides, we're going to just be using simple majority quorums. So let's delve into the details. Phase 1 of Paxos. A client chooses one of its allocated registers, so that's implementing the register allocation rule, and sends a message, prepare I, to all the servers, where I is the register set that it's going to choose to try to use in this phase. Each server that receives the message, prepare I, is going to write nil into any unwritten registers that it has from 0 to I-1. So that's doing the kind of freezing of the system state so far. It's preventing those quorums from reaching different decisions. And the server's going to respond with a register and the value that's contained within that register of the greatest register that's been written so far. The client's going to wait And once it's got a response from a quorum of servers, the client is going to choose the value v from the greatest register. If it didn't get any values from registers before, it's free to choose whatever value it would like. So then, the input to the second phase of the algorithm is the register set that was chosen in the first phase and the value that was chosen in the first phase. The client sends the message propose IV, so I is the register set, V is the value, to all of the servers. Each server checks if the register I is unwritten. If it is, then you write that value to that register, just like the client told you to do. And you respond with the message accepted I. As in the first phase, the client waits, and when they receive the accepted I message from a quorum of servers, they have finished, they have achieved consensus, and they are able to go away having learned the decided value. If in either of these phases the client ends up waiting for more than a defined period, the client can retry with a different register set number. So that was Paxos in 2 slides. We're going to go through some examples now. So here's a system. We've got 3 servers, S0, S1, and S2. And we've got one of our state tables from earlier that is going to show us what's going on inside these servers. Initially, all the registers are empty. Any of these quorums could decide anything. Client pops up into the system. They've been allocated the register R1, and so they're going to send the message prepare R1 to the servers. Upon receiving this message, the servers are going to follow that protocol that we saw before. They're going to write nil into any of the previous registers, which is R0, and they're going to respond with the greatest register that they have. In this case, they don't have any registers that contain values. So they're just going to say, promised to you in R1, end of. Once the client's received this message from 2 of the servers, the client is free to choose any value it wants to write in the second phase. We know that the previous quorums won't be reaching any different decisions because their state of all of them is just no, right? It's not going to reach a decision. So the client can safely choose any value it wants, and it unimaginatively chooses the value A. So then it sends the message propose R1 A, and that simply means write A into R1 if there's nothing already there. And so the servers will do as they were told. We can see in our state table we've now reached a decision, and the servers will let the client know. We accepted that write that you proposed. The client now knows that the value A has been decided and can go off and put that to use. Another client comes along into the system. This client, again, will follow the same protocol. It will send the message prepare, this time using the register R2. The servers, in this case, they will follow the same protocol as before. There is no unwritten registers, so there's no work to do on that side, but there is a register that contains a value. That's that register R1 that contains A. So the servers are going to say, I promise to you, like I've done this work of checking safety, and in register R1, I have the value A. Just letting you know that that is what's there, and that could potentially lead to a decision of A. Once the clients receive these 2 messages, it can proceed to the second phase. However, it is not free to choose any value it wants, because it knows the previous quorums might have decided A. Therefore, it's going to have to propose A during the second phase of the algorithm. The protocol proceeds as before. The servers write the value A into the register set R2, and then the servers respond to the client saying, we accepted that. This client then learns that A has been decided. This is not the most optimal version of Paxos. This was just the easiest to fit on one slide. So there is a couple of optimizations here that we can talk about in the questions if you'd like. So Paxos requires that any quorum that we're using, whether it's for the first phase of the algorithm, the second phase of the algorithm, whether the client's writing to register set R0 or register set R10. Whatever the client's doing, it must use a quorum, and all those quorums must intersect. And because we require all quorums to intersect, using majorities is a sensible choice of quorum system. But remember in our examples earlier, we weren't using quorums that all intersected. In fact, the quorum intersection requirement is much weaker than that. The only quorum intersection requirement, literally the only one, is that a client using register set I must get at least one server from each quorum of register set 0, so I minus 1, to participate in the first phase of the algorithm. That means we don't require quorums for the first phase to intersect. We don't require quorums for the second phase to intersect. We don't require quorums from my phase 1 to intersect with my own phase 2. None of those things are required. This is the only quorum intersection requirement. It means, for example, if you're writing into register set R0, you don't have a quorum intersection requirement because there are no previous registers, for example. So that's neat to know on a theoretical sense, but I'm not sure it's necessarily actually useful for anything. So in this section, I wanted to give you an example of an algorithm that puts this to work. So a weakened version of this result that just shows that you don't need intersection between the first and second phases is known as flexible Paxos. I've written a paper about that a few years ago, and people have put that into practice at optimizing multi-Paxos. But the example I'm going to give you today uses the full strength of the result. This is a vastly simplified view of what the world of distributed consensus looks like. There's classic Paxos, so that's the single instance Paxos algorithm. And that requires a minimum of 2 round trips to reach consensus. And then there's multi-Paxos, this leader-based optimization that is widely used in practice. This only requires 1 round trip to reach consensus. However, when it comes to who is able to actually reach consensus, in classic Paxos, any of the clients are able to reach consensus. However, in multi-Paxos, we have one of these special clients who's the leader, and we've said, you're the boss, you're in charge, you're the one who's going to make the decisions. If the client is that leader, then that's great. But if you're the other side of the world from that leader, that's not so great. In fact, you basically have an extra round trip to go and get to that leader. So the question is, can we design an algorithm that could give us both of these? That can allow any client to achieve distributed consensus and to do so in just 1 round trip? And this is what I'm going to look at in this part and with this algorithm called All Aboard. I'm going to start by making 2 observations about consensus systems today. Firstly, failures are rare. We want to tolerate failures, and we are not going to compromise. We will still be able to tolerate the failure of a minority of participants in the system and make progress. But in practice, that doesn't happen very often. So maybe we can make use of the fact that most of the time, most of the servers are going to be up. And secondly, when we look at algorithms such as Raft, they co-locate a server and a client on a physical host in the system. And they might call that like a replica, for example. So what this means in practice is that one of the clients has basically free access to one of the servers. They can ask the server, what's going on in your registers? Can you read those values for me? I want to write to those values. And they don't have to traverse the network to do it. So can we utilize these 2 things to build an alternative algorithm? Spoiler, yes, we can. So this is an example of what a quorum table might look like. Here we have 3 servers. And for a chunk of the register sets, in this case I've said the first 10 register sets, you have to use all of the servers. So you're going to use 3 servers instead of using 2. Distributed systems, you can't get anything for free. You have to pay a bit of a price. This is the price that we're going to pay. So you're going to use all servers instead of using a majority for these register sets. But for register sets 10 onwards, you can use majority quorums as you did before. The result of this is that we've given clients two different options for how to reach consensus. We've given them a fast path. In this path, a client can execute the first phase of Paxos locally, and then in the second phase, they get agreement from all the servers. So if we have 3 servers, you then need to wait for 3 responses. Or a client can take the slow path, which is basically just the classic Paxos algorithm that uses 2 round trips. We've got a new kind of best case, we've got a new option for clients. But if clients go into this algorithm knowing that one of the servers has failed, for example, just use the classic Paxos algorithm. You can fall back to the old algorithm, and that means we've not compromised fault tolerance at all. So in summary, this all-aboard version of Paxos allows any client in the system to achieve consensus in just 1 round trip. So imagine, for example, that your clients aren't right next to each other in a rack, but they're actually spread across the world. This means that in just 1 round trip, you would be able to reach consensus instead of having to do it in 2. The downside is that we've increased the quorum size from a majority of servers to all servers. But my claim for why this might be okay is that you would only use this in systems where you don't mind making this compromise. And secondly, we may need more round trips if one of the servers is slow or unavailable. The things I'd like you to take away from this talk is that immutability and generality can change our perspective on how we view distributed consensus. Paxos has been around for decades, but it doesn't mean it's the only option or the only solution to solving distributed consensus. And if you're using Paxos, you can relax its quorum intersection requirements, as we did in all aboard Paxos. By relaxing quorum intersection requirements, we can utilize different quorum tables, and these give us different trade-offs when it comes to reaching consensus. The algorithm I showed is not meant to be a new silver bullet. Like, use this algorithm absolutely everywhere and it will always be better than Paxos. Absolutely not. This is just to illustrate that there are different options. You may want to trade off a bit of performance in the steady state for performance when you're dealing with failures. Maybe you don't want to handle a minority of nodes failing. Maybe you'd be willing to handle 2 failures out of 7 instead of 3. It's up to you guys as engineers to basically make the choice of what you want to achieve in consensus and what you're willing to kind of let go and sacrifice for it. So Paxos, with its majorities, is just a single point on a broad spectrum of possible solutions to consensus. So today, I have only been able to cover a tip of the iceberg, really. This work has allowed us to basically revise Paxos and to come up with all sorts of interesting optimizations for the algorithm, and also expands to all sorts of other consensus algorithms. So we can use this immutable state to also represent fast Paxos, to also represent Raft, to also represent view stamp replication, ZAB, all sorts of consensus algorithms. Using this representation, it's a lot easier to compare the different algorithms and see, actually, in some ways, they're surprisingly similar, and in other ways, they've made really interesting different design choices. And this is discussed in this paper. The slides are online, so you can go find the link on there. Otherwise, you can just Google it. And if you don't fancy reading it, the morning paper covered it more briefly and better than I can. All right, thank you so much. That's it from me, but I've left plenty of time for questions because I know that's quite a lot to take in. So feel free to ask away. Can someone run around with a microphone? Yes.
Heidi, thanks for the talk. It was really nice. My question is, could you tell me perhaps something about implementation of Paxos, let's say in the scope of semantic web? Do you know something about with some practical solutions in knowledge graphs and semantic web? That's the question.
I'm going to be honest with you and say I know very little about the semantic web and noise graphs. I'm sorry. There's no applications of consensus that I can think of.
Because it looks like something that can be really applied there.
Yeah.
Okay.
I mean, it's widely used in practice. So systems you might be familiar with, something like Zookeeper, which uses the ZAB atomic broadcast, and atomic broadcast has been shown to be the same as consensus. Also, the raft algorithm has been really popular, and that's been used in linearizable key value stores, such as etcd and console, and they're used by things you might have heard of, like Kubernetes. But I'm not sure about the semantic web, to be honest with you.
Thanks.
Thanks.
Any other questions?
Thank you very much. That was an excellent talk. Question. So you started with FLP theorem.
Yep.
That basically says that consensus is not guaranteed.
Yep.
And then you said that there are multiple algorithms that actually make it work. Isn't it a controversy?
Yeah, that's a good question. So what the FLP result says specifically is that we can't guarantee the termination of these algorithms when the system is acting in an asynchronous manner and something might fail. And that's because the way that we check if something has failed is by asking, like, are you there? Are you alive? And if the system's asynchronous, that message may take a really long time to get there. We might assume it's failed when actually it hasn't, and then be unable to make progress. The reason why these algorithms work is because most of the time these failures don't happen, so they're able to proceed. And when we prove the progress of these algorithms and we prove the termination, we assume that the system, that all the participants are up and the system basically has reached a stable state, and then we show that they're able to work. But if you deploy Raft on a system where there's only ever one live node, it's not going to reach consensus. Good question.
I have a comment. You say that system cannot reach consensus. I have some mathematical research on base of Markov chain, but mathematical decision that it's never can never reach consensus in a non-stable system like instable network, overload servers. I tested in reality and also not reach consensus and found solution for reaching consensus eventually in a limited amount of time. It cannot be reached because only one vector used to reach consensus is number of iteration, number of register. In reality system, we can calculate another vector. It's hash of data. We, in case we cannot reach consensus because all three nodes has different value, or one node fail and two different has different value, we can choose less value of hash it can reach consensus. I make speaking of it on Hello 217 you can download its internet, but it's on Russian, but you can translate it Google Dictionary. I say hope can use it Markov chain to decision what is a consensus reached in eventually.
I'm sorry, I missed the question.
Okay. Okay. What?
Could you summarize the question briefly?
Oh, okay. I have questions about. I have questions, but it's
a follow-up
another question that
let's
my mind.
go to the discussion zone to carry this one on.
Okay, sorry.
No worries.
Thank you for lecture. And I have questions that you said that when client, each client assigned to a register set, and there could be other clients assigned to the same register set, or not?
No, so for the sake of this presentation, each client gets his own distinct set of registers that it can write to. So you might go round robin and say register 0, 1, 2, register 3, 4, 5, etc. Other algorithms do allow multiple clients to write to the same register set. So for example, fast Paxos doesn't have that requirement that each client only writes to one register set.
Okay, then other questions that if we have a client that has R3 that writes to nulls to R1 then R2 and goes smoking, so it's never writes value, and then we try to values clients that writes to R2. And there are null, but other client never writes value. So it cannot write value because they are null, it can proceed further. And other client never proceed further as well.
So yeah, so each client, when they get this disjoint set of register sets, of the registers, it should be kind of an infinite set in theory. So they can have register 1 and then they can try register 4. And if they're not successful, they can try again with a higher register set.
So it's not static, it's dynamic relationship, yes? Register set and client.
So the allocation of registers is a static one. And as a client, you would choose to use a low one, and then if you needed to, you'd go on to use a higher one. You can end up in scenarios where you've got a kind of dueling behavior, basically, where everyone, you go and you write nil, and then the next person comes and they write nil over where you were planning to write, and you can basically fight it out. But we can resolve that with timers and such. And there's actually some really good optimizations where you can detect that and then help the other client to reach consensus for themselves.
So our system couldn't go to the states where some client cannot do any work, yes?
Sorry, can you repeat that?
So the system cannot go in the state where some client cannot write value at all.
No, a client will always be able to write a value. This is why we have to, in theory, have an infinite set of registers, because you could use up your quorums when, for example, one of the nodes is down, two of the nodes in a system of 3 is down. You could basically use up your quorums by doing a bunch of writes. And the theory is eventually the system will stabilize and everything will be good. And so when the system is up and everything is good, we need the clients to have access to a register set to which they can write.
I remember my question. You make prediction what a system fail rare. Why such prediction? Because for example, in case of overloading, system can fail pretty fast. For example, it can lost every thread message sitting in cluster, for example, or every 4 message. It's absolutely real case with easy to reproduce. It's correct to make algorithm based on prediction what fail rare.
If I understand, I'm going to try and rephrase that. Was the question, when you have congestion in the network, so you've got a bunch of delay and asynchrony, your participants are all fine, but it doesn't look like they're fine. What happens then with the algorithm?
Yes, it's you say it's work because fail rare, but it's fact in emergency situation it's not just fail, it can fail up in multi-time in second even.
Yeah, so we can have, if we have, say, we're using majorities and we need 2 or 3 nodes to be up, what happens if it's going up and down, or that set, the 2 that are up are rotating in the set of 3, such that they're often different? Yes. it doesn't protect very well against that, is basically the answer. In terms of the conditions we use when we're proving progress, we are assuming we assume that everybody is up and everyone is okay for that bit. And otherwise, yeah, if it moves around too quickly, we can't make progress, no.
Can in practice waiting for all servers to answer be less efficient than preparing the second step of the algorithm? Are there some benchmarks?
Absolutely. So I think it completely depends on your system. It can totally be worse, especially if you've got one node who's really slow. They're alive enough that you're not switching back to general Paxos, but they're still there, so you're stuck waiting for them. So yeah, it totally can be worse than using majorities and possibly having to do it twice. It really depends on the system that you're using. So for example, if you're within a local area network, within a data center, or if you're across a big system. If you're using 3 nodes, I feel like the difference between waiting for 2 messages and 3 messages isn't huge. But if you're using many more nodes, if you're using 9 nodes, then you're having to wait for 4 extra messages, which is quite a lot of extra time, yeah. So it's not about saying that this is better. It really depends on the system that you're using.
So, Heidi, thank you. Let's continue in discussion zone. One small question, so sorry.
Last and small. Thank you again. I read a book of Nancy Lynch, Distributed Algorithms. It's an excellent, but it's hardcore mathematical rigor. Are you aware of any other book which is more about intuition? Because even though I understand math, I'm more engineer than mathematician.
I feel your pain. I'll just start by saying that. I also, I started this journey. It was long and painful. It was hard enough that I got a PhD in doing it. So we shouldn't expect all engineers to have to go through all of that just to learn distributed algorithms. It is a more practical angle, but Martin's book on designing data-intensive systems does a really nice kind of high-level overview of the intuition of some of these algorithms. And then if you're interested in the details, you can then look at papers and blog posts and go through the pain. But it's nice to just get a high-level overview of the intuition generally in distributed systems for a range of algorithms. And then when you're going to kind of go through that work, just do it for the ones that are actually important to you and that you really care about. No worries.